Okay, page 1 of Applications of Differential Calculus Addendum. First, there is a slightly more challenging problem for rates of change. A fish farm grows and harvests barramundi in a large dam. The population of fish after 2 years is given by the function p of t. The rate of change in the population, dp dt, is modeled by that function there, where a, b, and c are known constants. A is the birth rate of the barramundi, b is the maximum carrying capacity of the dam, and c is the percentage of barramundi that are harvested each year. Just to note, b, which is the maximum carrying capacity of the dam, that means the number of fish that can live in this environment, carrying capacity. Okay. Explain why the fish population is stable when dp dt equals 0. Well, what they're saying there is that the rate of change in the population is 0. If the rate of change of the population is 0, that means the number of fish is not changing, which another way to say that is the fish population is stable. It's not changing. So basically it's saying the same thing when you say that the derivative of the population equals 0. If the birth rate is 6%, the maximum carrying capacity is 24,000, and 5% are harvested each year. Find the stable population. Okay, so let's do that. We're going to take dp dt, and we're going to find it by plugging in some of these numbers they gave us. So let's see what numbers we have now. The birth rate is 6%. The birth rate is A. Okay, so A is 6%. Maximum carrying capacity, which is B, is 24,000. And C, which is the percentage that are harvested, is 5. Okay, so based on that, find the stable population. This book doesn't have too many mistakes in it. I don't know if this is a mistake, but I think this is pretty weird. If you are trying to get the answer they get in the back of the book, it's funny because normally when someone gives you a percentage, you kind of question, okay, how am I going to put the percentage inside of an equation? Am I going to just put the number in the equation, or am I going to multiply it times 0.01 and make it into a decimal? Well, they did something really odd here. The 6%, they multiplied times 0.01 and made it into a decimal. And then the 5%, which is the harvest rate here, the 5%, they just put in as a number. I guess because they have the 100 in the denominator here, they figured they didn't need it. So that's pretty bizarre. Usually they don't do something that inconsistent, right? So let's multiply it out. We'll have 0.06p minus 0.06 over 24,000 p minus 0.05p. So now I'm going to combine 0.06p minus 0.05p. I get 0.01p. And then I take 0.06 divided by 24,000 with the offline calculator. It gives me 0.0000025 p squared. I set all that equal to 0. Now, to see what values of p would make that 0, the easiest way to do it is to factor out a p and make 2 factors. We got p and 0.01 minus 0.0000025 p, right? So a p-value of 0 would make that 0, and the whole thing would become 0. But that's not a very interesting result because, oh yeah, a population of 0 fish is stable. Whoopie-doo. Okay? And then the question is, what value of p would make this 0? So to find that out, what we can do is we could subtract 1 over to the other side. And then we get this expression here, and then we can say, okay, what's the value of p? And we'll divide 0.01. We'll divide 0.01 by 0.0000025. and we get 4,000. So the value of the population that would make the number of fish stable would be 4,000 if the carrying the birth rate is 6%, the carrying capacity is 24,000, and the harvest rate is 5%. Now they say, what happens if the harvest rate became 4%? What would be the stable population then? So the only thing we're going to do is we're going to change this 5 to 4. We're going to change this 0.05 to 4. So let's do that. So we're going to do 0.06p minus 0.0000025p squared minus 0.04p. And 0.06p minus 0.04p is 0.02p. And then we're going to subtract that to the other side, so we'll get 0.0000025p squared. Oops. We forgot to factor out the p, but when you factor out the p, what's going to happen is you have no p here. Okay? Then we're going to divide both sides by 0.0000025. So it would be 0.02 divided by 0.0000025, and the answer is 8,000. Okay? Okay, now we'll do a optimization problem that is one which was in the HL book but was not in the SL book. You've already done many optimization problems, but maybe this one's I don't know, slightly harder or different. When a manufacturer makes X items per day, the cost function is C of X, blah, 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 dollars, and the price function is P of X, blah, 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 dollars per item. Find the production level that will maximize profits. Okay, one tricky thing here is we have a cost function, and they don't say per item, and then they have a price function, which they do say per item. So remember that if you're going to find the profit, you need to be consistent. So basically you want to say, okay, profit total is equal to price total. And when I say total, I mean like all items added together, minus cost total. And the other thing you could do is you could do profit per item equals price per item minus cost per item. Okay? So since the price function and the cost function are not both given in per item and they're not both given in total, you kind of need to decide on one or the other. So let's see. In this case, I think what's most applicable is you do total because they're trying to maximize the profits for the company. So it doesn't matter what the profit is per item. What you need is the profit per, for like the whole factory. So well, let's take the total price, which would be the price function, which is per item, and we're going to multiply it times the number of items, which is X. So the total price would be the price function, P of X, times X. And then we would subtract the cost function. And the cost function is already for the whole factory, so we don't need to multiply it times X. Okay? So that is the profit. The profit is P of X times X minus C of X. So we're going to fill all those in. P of X turns out to be 15 minus 0.002X. And then we subtract the cost function, put it in parentheses because we need to distribute that minus sign, which would be 720 plus 4x plus 0.02x squared. And then let's distribute the negative sign. So we'll have, and we'll distribute the x also, 15x minus 0.0002x squared. I'm sorry, it's not 000. It's just 0, 0. Minus 720 minus 4x minus 0.02x squared. Okay, we can remove the parentheses now. Now let's combine these two like terms. So we have minus 0.02 minus 0.002, so we put minus 0.022x squared. Now let's combine these two like terms, 15x and minus 4x, so that would be plus 11x, and then let's put the minus 720 at the end. So we got the profit function, and we want to know when the profit function is maximum, so we are going to take a derivative of the profit function. So let's take a derivative of 0.022x squared plus 11x. So that would basically be 2 times negative 0.022x plus 11, right? So that would be negative 0.044 x squared plus 11 would be the derivative function for the profit. We'll call it lucrative derivative. Okay. Oops. The derivative of negative 0.022 x squared should be negative 0.044 x. Okay. And then we set it equal to 0 because we want the maximum value. And so when we solve for x, we get 0.044 x equals 11. X equals 1 divided by 11 divided by 0.044, which is 250. So the optimum number of items to produce is 250. Okay, let's go to the last problem, which is number 23. A pump house is to be placed at some point x along a river. 2 pipelines will then connect the pump house to homesteads A and B. How far from M should point X be so that the total length of the pipeline is minimized? Okay. So this picture, if you couldn't tell, is like from the top. And this is the river. And then inland, you can find house A and house B. What they want to do is say, where do we put X so that we can like run pipe from X to A and X to B so that the pipe, the amount of pipe is minimized. That's a practical problem, isn't it? So what we're going to probably do is we're going to write an equation which takes the position of X from M, the distance from X to M. Let's call that, D. And we're going to translate D into the length of the pipe, which we'll call this piece and this piece, we'll call that like P. Okay? So let's say P is equal to 2 pieces of pipe. One of the pieces of pipe would be D here. And one of the pieces of pipe would be related to this triangle with a side that's D. It's the hypotenuse. So we could say, okay, one of the pieces is the hypotenuse of D and 2. So we could say the hypotenuse of D and 2 would be square root of D squared plus 2 squared, right? That would be this length of P. And then the other length of P between X and B would be, it would be related to D. It would be 5 minus D, right? Because the total distance M to N is 5. So this distance here would be 5 minus D. And then the hypotenuse of XB would be square root of 5 minus D squared. Oops, 5 minus D quantity squared plus 1 squared, which is just 1, right? And that would be equal to P. And then we're like, okay, how do we minimize P? The way we minimize P is how do we find the value of D, which makes P minimum? We can take the derivative of P with respect to D. So we're going to take dP with respect to dd. Oh, now I can see why people don't use D for taking derivative. dd. Oops. Okay. And then we can, first we'll simplify this a little bit. We'll have D squared plus 4 to the 1/2 plus, let's see, 25 minus 10D plus D squared plus 1 to the 1/2. Okay, and then we can combine 25 with 1 and get 26, right? And so now let's take the derivative of each one of the expressions. We're going to have to do chain rule, right? So 1/2 d squared plus 4 to the negative 1/2 times chain rule 2d plus 1/2 times 26 minus 10d plus d squared negative 1/2 times chain rule negative 10 plus 2d. Okay. And so we're going to see when this expression is minimized by setting it equal to 0. Now starts all that algebra that I warned you about that you're going to have to be really good at in HL Math. So let's multiply 1/2 times 2. We can cancel those out. We can multiply this 1/2 times 10 plus 2d, and we can make it into negative 5 plus d. And then we could take these expressions, d squared plus 4 to the negative 1/2 and 26 minus 10d plus d squared to the negative 1/2, and we'll put them in the denominators of these two fractions, and we end up with this interesting expression. And this is, of course, set equal to 0. So now what we want to do is kind of set them equal to each other so that we can square both sides and get rid of some of the complexity here. So we're going to move one of these to the other side. Which we can do by putting minus d minus 5, and then we'll put the same denominator to the 1/2. Then we're going to square both sides so that we can get rid of the root sign, which is really annoying, right? It makes things much more difficult. We can't combine anything with anything. Oops, I just took my river water. Okay, and then I'm going to square both sides, so I end up with d squared on top, and on the bottom I still have d squared plus 4. On the right side, I'm going to have d squared minus 10d, right? Because minus 5d plus minus 5d is minus 10d. Minus 5 squared is plus 25. This negative 1 here squares and disappears, okay? And then the bottom, 26 minus 10d plus d squared to the 1/2 is going to just be to the 1 because I've squared it, okay? Then I've got these two things equal to each other, right? And then I want to cross multiply them so that I can combine like terms. So I'm going to cross multiply that. I'm going to cross multiply this. And I'll end up with, on the left side, I'm going to multiply the two green ones, 26d squared minus 10d cubed plus d to the 4th on the left side. The orange side is going to be d squared times d squared, which is d to the 4th, d squared times minus 10d, which is minus 10d cubed, d squared times 25, which is going to be 25d squared. 4 times d squared gives us 40. 4 times d squared gives us 4d squared. 4d squared, not 40d squared. Oops. Okay, and then minus 40d plus 100. Now we're going to combine like terms on the right side. So d to the 4th minus 10d squared minus 10d cubed plus 25d squared minus 40d plus 100. Then we can start comparing the terms on the left and right side of the equal sign here. We can take out the d to the 4th because we have d to the 4th on both sides. We can take out the minus 10d cubed because we have minus 10d cubed on both sides. Then we are left with just a few terms, which would be, let's see, 0 equals, and then we'll have 26d squared. We can subtract that from the left side and the right side, so we'll end up with 3d squared minus 40d plus 100. And then we can see what the roots are for this using poly-SMLT. So we'll go to polysmlt, which you can get to by doing apps and polysmlt, and then you go to polyroot finder. You say it's a second order because it's a quadratic, and you do next, and then we say our coefficients are 3, -40, and 100. And then we solve. And we get two answers, 3.33 and 10. So we got distance equals 3.33 and 10. We look at the picture to see if either of those makes sense. 3.33 and 10. Oh, so 3.33 kind of makes sense. That looks like it might be 3.33. So what about the answer d equals 10? That doesn't seem to make sense because if d equals 10, the distance mx would be bigger than the distance mn, which is only 5. So we can discard the other answer, 10. Okay. Now it's a pretty big challenge to prove that 3.33 is a minimum instead of a maximum, because as you can see, it was already pretty difficult to work with the expression for dpdd, which is basically this expression here, right? In order to take the second derivative of that, you would get another ugly function, and it would be pretty hard to find the zero of that too. So in this case, you could kind of do it visually. You could say, okay, this looks like it might be the answer. If I start yanking the x point to here, is that going to improve things? Is the distance from x to a and x to b here, would that be shorter? And you can kind of do it visually. I don't recommend wasting time taking the derivative of this function because this is the type of problem that would be on the calculator portion. So what you would do probably is you would insert this function into the calculator and graph it, and then you could kind of see which concavity it is. So yeah, that is a mess. And one thing you do not want to do is you do not want to take the quadratic here, and like assume that that is the first derivative and take the derivative of that, because that makes no sense. This quadratic, although it is a equivalent to this expression 0 equals blah blah blah, we actually plugged in 0 in for the derivative, and then we cross multiplied and did all sorts of stuff. So this quadratic is not the same thing as this. The quadratic equals 0 is equal to this expression equal to 0. So what we need to do is go back to dy dx equals this, and then take the second derivative of this right side, which would be terrible. Okay? So not worth doing. All right? Just understand how you would do it. That's it.